Okie dokie, good morning chemists. We'll get started. So today we're going to finish up the last bits of chapter 20 that's left to do for midterm 4. That's occurring on Thursday this week. So you have one more recitation tomorrow. We don't have lecture or anything on Wednesday because of Juneteenth. And then yes, so an extra day to study. And then the last midterm on Thursday. And then we'll have lecture again on Friday. So we left off, so that's the plan. I don't have like a full lecture planned for today. We'll just finish up bits and pieces of chapter 20 plus a last bit of chapter 20 that'll help you for the VOL lab tomorrow. So we'll just touch on electrolysis. I'll show you how to do those calculations to help you for that VOL lab, and then we will jump into the midterm 4 review session. So get that packet and we'll review for that midterm coming up later this week. All right, so chapter 20, we left off talking about voltaic cells, spontaneous cells. I forgot to ask them to bring our little pinwheel here thing where we set up a copper tin voltaic cell and harnessed that energy that comes from spontaneous redox reactions. So we're doing some calculations here, and I wanted to show the calculations and relate it to some of the concepts we've been talking about. So when predicting the cell voltage of a voltaic cell or any type of electrochemical cell, once we identify what the cathode is and what the anode is, typically we take these values from table values that are given in the reduction potential form. We take the most positive thing and then subtract the most negative thing. And when we do that, we get the most positive value of E cell possible. And that's what we did on this slide. We identified that this gold reaction had the most negative reduction potential, so it's most likely to be the anode, while this most positive reduction potential between this IO minus compound was most likely our cathode because it's a very positive number. And so when you take a very positive number and subtract a very negative number, you get a very positive overall cell potential that comes out. So identifying what's the anode and what's the cathode is pretty straightforward. We're looking at those reduction potential numbers, but then we put those reactions together to give an overall balanced chemical reaction for the entire redox reaction that's happening. So we need to recognize that all of these values that are given are in the reduction potential form, but in a redox reaction, something is reduced, something is oxidized. So we have to flip this the anode reaction because it is actually being oxidized in our electrochemical cell. So we did that. We flipped this reaction, all right, and added the oxidation reaction to the reduction reaction as written because it's already in the reduction form, and then multiplied by the appropriate multiplier to get those electrons to cancel. So I want you to recognize that, okay, this is our reduction reaction. We got it from the most positive reduction value. Things that are reduced are oxidizing agents. So I want to pick a different color here. So that means that this compound, IO minus, is the best oxidizing agent in this group because it has the highest reduction potential. It's the most positive reduction potential. All right, so let's translate that to the other reaction here that we chose. The other reaction are the reaction that's happening at our anode. That would make this gold compound, because that's what's changing its oxidation number in this reaction. This gold compound is going to be the best reducing agent because it is being oxidized in this reaction. So best reducing agent, and it's because our reduction potential is the most negative, so it's the smallest reduction potential, but that also means that its oxidation potential is very high. That's most likely gold in the solid form has a very high oxidation potential. But notice when comparing this to the values that are actually given initially, we have to deduce that, okay, in order to identify a reducing agent, which is something that's oxidized, we're looking at the reverse of the reaction. So if we relate this oxidation reaction to what's given in this question, gold solid is a great reducing agent, but it makes this gold bromide substance a really crappy reducing agent, or sorry, a very crappy oxidizing agent. Basically, it's very easy to oxidize gold, but it's very hard to reduce this gold bromide compound. And we can tell that because it has a very negative non-spontaneous reduction potential, therefore its oxidizing potential is very, very positive. So it's kind of the same idea as, you know, in chapter 16 and 17 we said, okay, if you have a really strong acid, its conjugate base is a really crappy base, versus if you have a really crappy acid, its conjugate base is really good. And so it's the same idea here. When you think about a reduction reaction that's not very favorable, the opposite, the oxidation reaction, is going to be very favorable. And so we're going to relate these numbers to then where we left off here is this slide. All right, so we did this earlier, kind of doing that same thing. What is the strongest oxidizing agent and the weakest oxidizing agent? These oxidizing agents are things that are reduced, so we go ahead and just use these tables and reduction values as is. But when we want to think about what is the strongest and weakest reducing agent, we actually want to look at the oxidizing potential, so the reverse reactions here. So the answers to these two were the strongest reducing agent is the one that is the reaction that's the crappiest at being reduced. So in this case it's zinc, but remember it's the reverse reaction. Zinc is being oxidized to zinc 2+, therefore it's a very strong reducing agent. Same thing for weakest reducing agent. The weakest reducing agent is the product of the substance that is easiest to reduce in this case. So silver plus to silver solid, really easy at being reduced. So this direction is very favorable, but going in the opposite direction, silver to silver plus, is very, very difficult. So that would be the weakest reducing agent since it's a thing that's being oxidized. All right, so another way to kind of ask similar conceptual questions here would be, okay, H plus can oxidize which one of these species? So I gave you all the tables of all these reduction potentials, so what we want to analyze is, okay, what's my anode, what's my cathode? We are generally looking for cell potentials that are positive. All right, but we need to figure out what is our cathode, what is our anode. So in this case, H plus is oxidizing something. So H plus is the oxidizing agent. Therefore, if it's the oxidizing agent in a redox reaction, H plus is going to be reduced in this reaction. So remember, agents, they do the opposite. So like we have the opposite answers there, where an oxidizing agent is a thing that is reduced in a reaction, where a reducing agent is the thing that's oxidized in a reaction. So if H plus is being reduced, it means that H plus is my cathode. So I'm asking, okay, which one of these things is my anode to give an overall positive cell potential? Right, so if these things are my anode, they have to be oxidized in the reaction. So there's some of these things that we can eliminate right away. All right, when something is oxidized, how does its oxidation number change? It goes up, So if we look at some of these things, because look, there's two forms of copper here, there's two forms of lead. Only one of those forms can actually be further oxidized. So we can actually eliminate these two, copper 2+ and lead 2+, because they can't be oxidized more. So basically I'm asking, so H plus can only oxidize, further increase the oxidation number of either copper or lead. We just need to figure out which one. So in this case, we can't oxidize these cations further. We're going to look at these neutral species. So if these substances are the anode, they are the second component here. So if we look at this table and see, okay, where is copper in this table? So right there, and we see lead is right there on this half reaction list, and then those are our two reduction potential values. So you know, we can write these down here. The reduction potential of copper is equal to positive 0.337, and for lead, the reduction potential is negative 0.126. So if we combine this with the reduction potential of H+, which is going to be our cathode. So I'll just highlight that right here. When we plug in these values into this cell potential equation, we're taking 0 and subtracting some number here. And so in only one of these examples will the number that comes out when we either plug in this reduction potential or this reduction potential, we see that lead is the only option that a positive overall cell potential comes out. So that means H+ can oxidize only lead 0 in this case. So what we would see, what we observe here, like if this was the activity series, is that lead solid dissolves in acid, but copper doesn't. All right, and so kind of like the example we talked about earlier, that you know, the reason why lead pipes are such a concern is because it is a spontaneous reaction. That lead solid does in fact dissolve in acid because a positive cell potential comes out, but you don't have that worry with copper pipes because it has a negative overall cell potential, so it's not spontaneous. All right, so let's just do the last one here, but see how the wording is different, but we want to use the same strategy. Here, I'm asking copper can reduce which of these species. So copper is acting as a reducing agent. So therefore, copper is being oxidized in our reaction. It is going to be our anode. So you can go ahead, let me just delete all these things. Copper is what's staying constant here. All right, so copper is going to be our anode, so we already know what number has to go into this anode component. It's going to be, we're going to subtract that positive 0.337 value. But what is going to change here is what is our cathode. So something here is going to be reduced. It is going to be our cathode. So the same idea as the previous one, only some of these things can actually be further reduced. Here we have lead 2+ and silver+. They have positive oxidation numbers that can further come down. They can further be reduced, while the solid lead and the solid silver cannot be reduced further. Because they're already a 0 oxidation number. You're not going to find lead minus or silver minus in these cases. So we can eliminate half of these examples. So same idea here. We want to look up those reduction potentials for lead 2+ and silver+, and we can see, okay, for lead 2+, it's negative 0.126, and for silver, it is positive 0.7794. And so if we put those two values into our equation, we can see, okay, in what scenarios can a positive number come out here. So let's see, if you put that lead value in here, doesn't a positive number come out? Does a positive number come out? Yeah, it does. So this answer actually should also include lead 2+. Sorry about that. Lead 2+ should be there as well. If you take negative 0.126 and, oh no, we're subtracting a positive number. Never mind. No, lead 2+ isn't an answer. I'm sorry about that. So if we take a negative 0.126 and subtract positive 0.337, we do in fact get a cell potential that ends up being negative. So in this case, no, copper solid cannot spontaneously reduce lead 2+. But if we use the silver example here, if we plug in that 0.77 number into that spot instead, we do get a positive cell potential come out. All right, so yeah, our only answer here is silver+. If you mix together silver+ and copper solid, you will see a spontaneous reaction happen, but it's all about the wording here. You know, I'm saying, okay, copper solid is my reducing agent. So which one of these substances are going to be reduced? So you have to kind of come to that conclusion that we're looking for the reduction potentials of the given list, while copper solid is our anode. It is being oxidized, so it's the second component of this equation. All right, so that's how we can use this standard reduction potential table. Remember, they're always given in the reduction form, but in a redox reaction, something is always reduced, something else is always oxidized, which is an oxidation reaction is the reverse of that, of a reduction reaction. All right, so there is our redox voltaic cells. So I mentioned this earlier at the beginning of chapter 20, the idea of if it's a demo that I've seen like done in front of children where they take two nails, shove it into a potato, and they light up a light bulb. All right, and they show it to children. They're like, look, a potato, we can make energy from a potato. All right, it's something that I've seen. I've seen this demo a lot, and you know, kids are not smart, so they think energy comes from potatoes. But I wanted to just kind of look at the kind of background information of this demonstration that might be overlooked. But since we're learning about electrochemistry, I will show you how this demonstration works. So what the demo person, when we're doing it in front of children, what we don't tell them is what we shove into the potato. All right, so the kids, they think the potato gives the energy. But when you set up this demonstration, or if you look closely here, what you're shoving into the potato is a copper penny and a galvanized nail. So galvanized nails and galvanized screws are made of zinc, or there's like zinc incorporated into it. So if you look at our reduction potential table, look, copper is right here, zinc is right here. So if you look at these two reduction potentials, we can see, oh, if copper is my cathode and zinc is my anode, if you combine those two things, yes, you in fact get an overall cell potential that is positive. That's what we did with the little pinwheel spinning, all right? The only difference is, you know, when I did that spinning pinwheel, I put the copper component and the copper and the zinc component next to each other via a salt bridge. But what the potato is actually doing is acting as the salt bridge itself. It's just acting as the medium, allowing those electrons to transfer to complete that circuit. So what we see here is that the energy that's produced in this experiment does not come from the potato, but it actually comes from the redox reaction between copper and zinc, but we don't tell children that. They make them think that the energy is coming from a potato. I tried so hard to get this demo to work, and I kind of got it. All right, I stole from the demo lab a copper strip and a zinc strip, and I went home and like got LED lights and was trying to get it to work, and I just barely got it to work with a pickle. I was able to do it with a pickle because pickles have tons of water in them. They're very salty, so it would act as a good salt bridge. I got it to work, but the light was so dim that I don't think it would have made an impact. So I was able to get a light to light from a pickle. But you know, they do this demo with potatoes and children. I just think that this graph is funny. I found it was like some student science fair or something, and I just think it's a really funny graph. One, I don't even know what these units are. Voltage, amps, like those are two different things. Voltage is one thing, amperage is current, that's something else. But I think it's really funny that this student, when they did their science fair project or whatever, they did a sweet potato, a russet potato, and a red potato, and they got different voltages for each. But what we're learning here, it's the potatoes that's not giving the energy, or making the cell potential. It's the nail and the copper piece that are doing the redox reaction. But I was wondering, why is the russet potato like higher than the rest? And I was like, oh, maybe there's a higher water content or something, and it just made the salt bridge more effective. But no, russet potatoes actually are a very starchy potato, so there's not a lot of water in it. So I don't know how the student got all of this data. It makes no sense. I just wanted to share it because I thought it was a funny graph. All right, so no, potatoes can't solve the world energy crisis. They are just acting as the electrolyte, the salt bridge in this reaction. Again, you can use a pickle. You could just use salt water too. You just put a copper strip and a zinc strip in it and connect a light bulb to it. You might be able to get something. All right. Okay, so yeah, potatoes can't do that. All right, so I'll point out that we'll work with this table a lot. Standard reduction. These standard reduction potentials. Just like when we used thermodynamic data in chapter 19, remember those thermodynamic data and these reduction potentials are all at standard conditions. What does standard conditions mean? 1 atm, 1 molarity of everything, 298 Kelvin. That's what standard conditions mean. So we'll measure these reduction potentials if the concentrations of zinc 2+ or copper 2+ are 1 molarity. So what the next section is, well, what if we're not at standard conditions? All right, what if we're not at standard conditions? How do we calculate the new cell potential? Because we don't have to build batteries at one molarity or 1 atmosphere. We can pack more concentration into things, and what we end up getting are different cell potentials based upon the concentrations of things. So this section is actually very much closely related to free energy, and a lot of these equations look very, very similar to one another. All right, so this is the last section that's on the exam, is calculating or relating free energy to cell potential and calculating a cell potential at non-standard conditions. All right, so let me just clarify some things about, okay, what exactly is voltage, and then we'll talk about current in a little bit. Right? So current and voltage are two concepts related to electricity. You know, if you do any electronical hobbies or crafts, you'll see those terms discussed a lot. So the difference here between voltage and current is, an analogy I like to use is like a waterfall. If you think of a waterfall and the flowing of water, where the water droplets are electrons, a voltage is like how high your waterfall is. All right, it's like the amount of work that can be done. The amount of energy transfer that can be done is based upon the height of the height difference where the water starts and where it ends when it free falls is like voltage. That's oftentimes why if you do electrical work, you'll talk about a voltage drop, and that's typically what it's referring to, kind of like a waterfall. Current, on the other hand, talks about how fast or how many electrons are passing through a certain point at a certain time. So current is like how wide your waterfall is. You can have a really, really wide waterfall, but with a tiny, tiny like drop, like a tiny lip. So you can have a really high current but low voltage drop, or you could have like a tiny little stream of water, so a very small amount of current because you're only transferring a small amount of water, but a really large voltage drop. So that's the difference, where current is just talking about how many electrons are passing through a certain point per second. For the most part, we've only talked about voltage or EMF. This is where our E-cell equation comes into place, where we relate this to voltage. Current is something completely different, where we have to set current a different way. But usually what helps chemists and scientists measure current is the idea that electrons carry charge. We can't see electrons. We can't count how many electrons are passing through a point at a certain time. But what we can do is measure charge separation. So what's going to come up in a little bit is this idea of Faraday's constant. Faraday's constant is given to you on the exam. Faraday's constant is a really large number. It's 96,000 coulombs. So that's how much charge 1 mole of electron carries. So what I like to do is, you take Faraday's constant, use it as a conversion factor, where Faraday's constant, so Faraday, 96,485 coulombs are in 1 mole of electrons. So if you know how much charge is being delivered, you can convert that to the number of electrons. Or if you know how many electrons you want to deliver, you can convert that to the amount of charge you have to deliver to a reaction. So recognize that this is the conversion factor that comes from Faraday's constant. That'll be very useful coming up. All right, and it's present in a couple of equations that we'll be using in a little bit. But Faraday's constant is given to you, and it's related to the current of that reaction. Okay, so let's bring all of the pieces together. Okay, so when we were talking about voltaic cells, these were spontaneous cells, all right? Spontaneous cells, these are reactions that happen on their own. They are spontaneous reactions, like a battery. A battery, you put in a battery into, you know, some electrical device, it discharges on its own. So the question is, well, why are only positive cell potentials spontaneous? It actually has to do with Gibbs free energy. What kind of sign for delta G were we always looking for? Negative signs. So what we have here is an equation that relates cell potential to Gibbs free energy. We want positive cell potentials. So that means delta G is negative for all of these spontaneous reactions. And so these are the equations that help us make that relationship. What we see is that the Gibbs free energy change for reaction is related to the negative N. So N is number of electrons. We've talked about this before. Number of electrons in a reaction, times Faraday's constant, times the cell potential for that reaction or half reaction. So what we see is that, yeah, if we put a positive E value into this equation, we get a negative delta G come out. So that's where that relationship comes into play. We want positive cell potentials. Those are spontaneous because it relates to negative Gibbs free energy changes for that reaction. All right, so why are only positive cell potentials spontaneous? It's because delta G is negative at when it's positive. So what we see is that this chapter is actually very much related to chapter 19 since we found that cell potential is related to Gibbs free energy. Where all of these things are connected to one another, all right? We talked about cell potential in this chapter. Last chapter, we talked about Gibbs free energy. But remember, Gibbs free energy is also related to K, the equilibrium constant for reaction. So this was from chapter 19, where the Gibbs free energy change for a chemical equilibrium is equal to negative RT natural log of K. So if delta G and K are related and E is related to delta G, what we see is that cell potential is also related to K as well. All of these things are interconnected via a couple of equations which we will be given on the exam. So just to kind of organize everything, we already talked about the cell potential equation where we take cathode minus anode. The new equation here relates cell potential to Gibbs free energy. And so don't forget that negative sign there. That's how we get that relationship. And then finally, we have a new equation that relates cell potential to K, our equilibrium constant. So we see that E is related to equilibrium constant by a factor of R. So the energy version of R. So the R that we use totally on this slide is the energy version of R. So 8.314. Joule mole Kelvin. Temperature, that temperature should always be in Kelvin. N is the number of electrons involved in that redox reaction. It's the N value we've been getting all of this time. And F, Faraday's constant. So Faraday's constant's coming in here. It's how we go from the energy realm of things to the voltage realm of things. So these equations relate E to K to delta G. All of those things get related to one another. But notice that all of these equations are related to one another when they are at standard conditions. So what I forgot here was E naught and delta G naught is related to K, the equilibrium constant for a reaction. And what we'll look at it a little bit later here is how to calculate cell potential at non-standard conditions. So this is how we relate E. So note that this E cell does not have a naught on it, and that's because it's not at standard conditions, just like delta G. I talked about delta G naught and delta G. Those are two different values. It's not a mistake when I write those values down. Typically, when I talk about delta G without the naught, we're not at standard conditions, so not one molarity of everything. So same thing with E cell. This is related to the Q of the reaction, so the concentrations that are actually there that aren't necessarily standard conditions. So what we get is the Nernst equation. All right, to calculate E cell at non-standard conditions is you take the E cell at standard conditions. So note that to calculate, to use the Nernst equation, you still have to do cathode minus anode using those table values. That's what this value is. But what we're going to do is subtract this value of log of Q. So we're going to take the concentrations that are actually there and adjust for those concentrations to get a new cell potential out. If you squint your eyes, this Nernst equation, doesn't it look very similar to the delta G equation that we did back in chapter 19? It's because they are the same equation, where in order to calculate delta G at non-standard conditions, you start with delta G at standard conditions and then just account for the Q, the concentrations that are actually there. So it's the same way the Nernst equation works as well. Take account for those concentrations that are actually there. All right, so let's get into calculations. Okay, so why is the Nernst equation and calculating voltages at non-standard conditions important? Well, it's because once we start a redox reaction, once we start a voltaic cell, a reaction is happening. So even if we start a reaction at standard conditions, it's not going to stay at standard conditions forever. So let's think about it. Let's pretend we are doing the zinc-copper reaction again. I set this up the other day with the little spinning pinwheel, and we measured the cell voltage, and we saw, okay, when zinc was in contact with this copper solution, then we got a measured voltage of 1.1. But the important thing was that this zinc 2+ concentration was 1 molarity, and this copper 2+ concentration was also 1 molarity. Because again, how we got that 1.1 volts was taking the reduction potential table, doing cathode minus anode, but since it's at those values are at standard conditions, everything needs to be at 1 molarity. So this is 1 molarity, this guy is 1 molarity. But we talked about this earlier, all right? So a reaction is happening. So will this copper 2+ stay 1 molarity? It's not going to. So how is that concentration going to change with time as this reaction's going to go? Yeah, it's going to go down. Versus the zinc 2+ concentration changes how? It goes up. So we see even if we set up this reaction, so we're at standard conditions, 1 molarity, 1 molarity. It's not going to stay there. So when we set up this reaction, Q is actually initially 1 when we're at standard conditions. So at standard conditions, Q equals 1. And that's common. We saw this before back in chapter 19. But again, a reaction is happening as this reaction goes. So what we see here is, okay, we start with 1 molarity at standard conditions, but as this reaction runs, we see that zinc 2+ concentration increases. And it's because zinc 2+ is a product. We said that copper 2+ concentration decreases because copper 2+ is a reactant. So therefore, based upon how those are changing, how does the value of Q change away from 1 as this reaction proceeds? Based upon our answers right here. The value of Q goes up because the numerator is increasing in value and the denominator is decreasing in value. So what we see is that Q, the value of Q increases as the reaction runs further and further and further, all right? And so now if we insert that Q into the Nernst equation, so let's think about this. When we start at standard conditions, what is log of, so at standard conditions, Q is 1. What is log of 1? 0, yes. So our measured cell potential, this E, is what we actually measure. When we're at standard conditions, log of Q is 0 because Q is 1. So we see, oh, what we measure is the table values because we're at standard conditions. But once this reaction runs, log of Q becomes a bigger and bigger and bigger number. If you just test it in your calculator, do like, log of 1, log of 2, log of 3, you see that the number gets bigger and bigger and bigger. That logarithm number gets bigger as Q gets bigger. So what we see here is as Q increases, log of Q also increases. So what we are doing is subtracting a bigger and bigger number as the reaction proceeds. So when we actually measure the cell potential as this reaction goes further, we see that the measured cell potential decreases. And that should make sense a little bit because, like, what do batteries do eventually? They die. Why do they die? It's because a reaction's happening, you're spending reactant, you're making product, Q is getting bigger, you're subtracting a larger value of log Q until your voltage approaches 0, and now your battery is dead. All right, so that's the idea here. As you spend your reaction, concentrations change, Q increases, your measured cell potential decreases because you know, your battery's approaching being dead. All right, so let's do a calculation using the Nernst equation. Okay, it's not that bad. The only idea here with the Nernst equation is first you have to do cathode minus anode. First you have to use the table values first, and then you just need to account for Q. So here, let's calculate the cell potential generated by this voltaic cell for this reaction at standard conditions. So since we're at standard conditions, we don't need to do the Nernst equation. Standard conditions just means use the table values, right? So if at standard conditions, all of these things are 1 molarity. So we simply need to identify what is our cathode, what is our anode, do cathode minus anode. So just looking at these numbers, there's only one way we can make those overall positive cell potential, where I think the top one has to be my cathode, and then the bottom one has to be my anode, right? And I think that's true. If you look at the overall reaction that's given, so up here, this is the overall reaction. Notice how this dichromate compound is here and it's there. So this dichromate compound is being reduced. This is being reduced. And then the I minus is being oxidized in this case. So yes, it matches what is our cathode, what is our anode. So if we do that subtraction, 1.33 minus the anode 0.54, we get a measured cell potential of, it's right there, 0.79 volts, all right? So that's what we should measure if all of the concentrations are 1 molarity. That means that we're already at standard conditions. We go ahead and use the table values. All right, so now the next question is, well, what if we're not at standard conditions? What if these are actually the concentrations of the battery or whatever, you know, voltaic cell we're making? So here are actual concentrations. Our strategy here is, what is Q? Given these actual concentrations, we actually need to calculate Q. So notice that I gave you the overall reaction already. So we need to figure out what is the equation for Q. So I know we put K in our back pocket for a while ago, but remember big K is just products over reactants with the appropriate exponents. So in this case, Q is going to be the concentration of the products over the concentration of the reactants. So it's simply going to be the chromium 3+ concentration squared. Nothing else, right? Right, nothing else, because everything else is a solid or a liquid on the product side. So it's just chromium 3+ concentration squared. Then over the reactants, so over the dichromate concentration to the 1, the H+ concentration, yikes, to the 14th power. There's a lot of them, there's a lot of H+, and then your I- concentration to the 6th. Perfect. So that is Q, or the equation for K. If we were at standard conditions, all of those brackets would be 1 molarity, so Q would be equal to 1. But here we actually have real concentrations. So I'm going to go ahead and place those numbers in. So there's the chromium concentration, so 1 times 10 to the negative 5, but it is squared. Do not forget that square. Chromium concentration, 2 molarity, not squared. H+ concentration is 1. Thank goodness, because it's to the 14th power. And then the I- concentration is also 1. So 1 molarity to the 6th power. So we can just ignore the rest of the things that are in the denominator because they're 1 to an exponent. So if you put that into your calculator, you get Q as a fairly small number. It's 5 times 10 to the negative 11. All right, that's Q. That's the ratio of reactants and products of this actual given cell, not at standard conditions. So that's going to help us with our Nernst equation. We have the value of Q. We actually already have E naught. This is our standard cell potential that we calculated earlier here. Now the only thing that's missing is N. N is the number of electrons transferred in this redox reaction. So this is the hard part. You have to figure out how many electrons are being transferred into this redox reaction. So if we look at probably the easiest way to do this, there's two ways. You can either look at the overall balanced equation or look at the two redox reactions that you're adding up. Notice that the cathode involves 6 electrons and the anode involves 2 electrons. So just pretend you are going to add up those two reactions to get an overall reaction. Right, you have to flip one of them and then multiply by a factor to make the electrons match. And you just need to ask yourself, what would that number be? What number of electrons would you try to make them both be so they would cancel? What would it be? 6. Yeah, so N is 6. And so how we would do that is notice that, okay, there's 6 electrons here. I need to multiply this reaction, the anode reaction, by 3. And flip it to make it 6 so they cancel. So that means N is equal to 6. You don't actually have to do it. You just have to look at those values and see what you would have done. Another way to do it, okay, so we're saying, oh, this reaction, 6 electrons are being transferred. Let's look at the overall redox reaction. Just look at one of them. Let's look at an easy one, I minus. 6 I minuses are becoming 3 charge neutral I2 molecules. All right, so we're going from an overall -6 charge here to a 0 charge over here. How many electrons does that take to happen? 6, right? Yeah, 6. So it matches the overall balanced reaction too. So there's another way you could do it as well. All right, so there's N equals 6. So now we just plug in everything that we know. We're going to use the standard cell potential that we used from table values. We're going to use Q, and we're going to use that N equals 6 that we just got previously. So the measured cell potential that we actually get from this cell is 0.79 minus 0.0592 volts over N, which is 6. Log of Q, so 5 times 10 to the negative 11. And so what we see here is that the cell potential that we actually measure with these different concentrations is a little boosted. That happens when we kind of cram a bunch of product in, cram in a bunch of reactant into this reaction and not a lot of product. What happens is that we lower the value of Q because we have a lot of reactants, and the cell potential that we actually measure is fairly high because there's lots of reactant there to give us the cell potential that we desire. All right, so that is your measured cell potential from the Nernst equation, that we are able to improve the voltage by 1/10 of a volt just by changing those concentrations. All right, what else did I want to say on this slide? Nope, that's basically it. So this is very similar to our work with Q and Gibbs free energy in the previous chapter. Oh, actually, yes, what I did want to mention was this Nernst equation. So this Nernst equation, let's go up here. All right, so here's 2 different versions of the Nernst equation. So electrochemists and analytical chemists, they don't like logarithms, they like log scales. So this Nernst equation, remember, is the Gibbs free energy equation, just in terms of voltages instead. So they put this logarithm in log of Q instead of natural log of Q. And so when they do that, this factor of 2.3 comes out. But there's still this RTF term that's there. But because most of these things are constants and temperature is usually 298 Kelvin, we just make it very easy for you and do the R, the T, and the F all for you together. And then what comes out is this term right here. So this is the Nernst equation that we're typically going to use because most reactions we do is at 298 Kelvin. It's at room temperature. So we just went ahead and did the RTF math for you to get you this 0.0592 volts over N log of Q. So that's where that came from, this version of the Nernst equation. But you can use the Nernst equation at any temperature. Again, we just make it easy for you and use this equation instead because it's a lot simpler. All right, so let's do one more here. A little bit different. So it looks like we are still working with the exact same redox reaction, this chromium thing. All right, and there's our standard cell potential, standard for this redox reaction. So how else can we use Q? Or how else can we use the Nernst equation? So here I'm asking you, okay, calculate the pH when we have the following concentrations and we measure this cell potential. All right, so notice that what we're measuring, 0.81, is not necessarily what's given here as the standard cell potential. So in this question, we're kind of approaching it differently. I give you what we measure. E is like what we measure given the actual concentrations. E naught, that's what comes from the table values. So in this case, I give you E, I give you E naught. We already know what N is. So in this case, we need to figure out what Q is. What is the required Q we need, the concentrations we need to give this particular cell potential? That's a little bit different from standard conditions. Remember, pH, I know it's been a while, pH is just a measure of how much H plus is present in the solution. pH is just negative log of H plus concentration. So really this question is asking what is the H plus concentration needed to give this cell potential? Because if we look at Q, the value of Q, I give you how much chromium you have, I give you how much dichromate you have, I give you how much I minus you have. Really, if we use the Nernst equation to calculate the required Q, we can back calculate what is the required H plus concentration to give that Q. So that's the idea here. Instead of giving you concentrations and you calculate cell potential, I'm giving you the cell potential, you calculate Q and the resulting concentration that you need. So we're working through this question backwards. We're doing our measured cell potential equals the overall cell potential at standard conditions minus this 0.0592 volts over N log of Q. We are solving for Q in this case, so let's put in those numbers. We measure a 0.81 volts, but it should be a 0.79 volts at standard conditions, 0.0592 over N. Do you remember what N was? 6, yeah, in the previous slide. Log of Q. All right, I'm just going to solve for Q and then put the concentrations in to make it easier for me. So if you do some subtraction and moving around, I think you get positive 0.02 volts equals positive 0.0592 over 6 log of Q. So I subtracted this point, I subtracted this over there. Oh wait, no, that negative is still there. Yes. That negative is still right there. Okay. Right? And so moving some things around, I think we get that log of Q equals something, what does it equal? Negative 2.2027, I think. Let's see, let's just check. I wrote it down, but okay, so 0.02 times 6 divided by negative 0.0592. Yes, negative 2.027, yes. All right, so that's log of Q. Remember, this is a log scale. Back when we were doing delta G, it was a natural log where you took E to the both sides. But in this case, because it's a logarithm, we're going to go back to 10 to the both sides. So that's how we undo the logarithm. And so we get Q is equal to 10 to the negative 2.2027. So Q is equal to, what is it? 0.009396. That is what we need. That's the ratio of products over reactants we need to achieve this cell potential. So we're now going to shove that all those concentrations into that Q expression. So Q is equal to 0.009396. And this is equal to the chromium concentration over all of that reactant concentration, but we're going to solve for that H plus concentration. So let's just go ahead and place all those concentrations that are given. So the chromium concentration is 1 times 10 to the negative 5. That is squared over the dichromate, so 2 molarity, not squared, we are solving for H plus, and that is to the 14th power. And then the I minus concentration is 1, so just 1 molarity to the 6th. So we can just ignore that, because 1 to any power is just 1. All right, there we go. All right, so let's move some things around to isolate that H plus concentration to the 14th. All right, so I'm going to multiply both sides by H plus to the 14th to put it on the other side. I'm going to divide all of this stuff from one another and then divide that value of Q out. So this is going to be 1e to the negative 5 squared over 2. So divided by 2, divided by 0.009396. And so we see that H plus to the 14th power is 5.32 times 10 to the negative 19. All right. So how do we undo that H to the 14? Should we find the 14th root power in your calculator? No, that you probably won't be able to find that. So to undo H plus to the 14, what you're going to do is take at both sides to the 1 over 14th power. 1 over 14. All right, so that number that we just got, I will take it to the 1 over 14th power. Don't take the time on your exam to try to find the 14th square root power on your calculator. You won't find it. This is just the quick way to undo that 14. All right, so what we get when we undo that 14th power, we get the H plus concentration is 0.256 molarity. All right, that is a fairly high concentration. That's not quite our answer. We need to get a pH, so you just negative log that number, and you get that the pH has to actually be less than 1. It has to be a 0.59 pH, so it's very, very acidic in this solution in order to get that cell potential. So in this case, we're using the Nernst equation to calculate Q and then a certain concentration inside there. Notice that there's just one variable, but make sure you know where to place those concentrations, Q, what cell potential you actually measure, and then what cell potential comes from the actual table values. And that's how we use the Nernst equation. All right. So how else can we use some of the concepts from chapter 19? So remember, we can calculate cell potential at non-standard conditions because we were able to do the same thing with delta G. But what we'll see here is that the cell potentials we measure, using table values or whatever, related to delta G, and they're related to K, your equilibrium constant for that reaction. So let's look at this redox reaction. We're taking silver solid, reacting it with oxygen and some acid to get silver plus and water. So with this equation, or this redox reaction, we are, instead of calculating at non-standard conditions, we are going to focus on the Gibbs free energy and equilibrium constant for this reaction. So we're just going to be using some different equations here. Notice that your cell potential for this reaction is related to the overall, the Gibbs free energy of the reaction. And we already know Gibbs free energy is related to equilibrium constant. So our strategy here is to first calculate what is the cell potential of this reaction. We have to get N as well, and then calculate delta G, and then calculate K from those results. So notice here what's happening. We have two reduction reactions. This top reaction is most likely to be the what? The cathode or the anode? Cathode, yes, it's going to be the cathode because it's positive. And then the bottom one is the anode because it's more negative. Also look at the reaction. Okay, so the top one is the cathode. O2 is, yes, the reactant. All right, because remember the reduction reaction stays as is, but silver plus, I should be highlighting this in a different color. Silver plus is on the wrong side, so notice how the anode reaction actually gets flipped before you get to that balanced chemical reaction. So yes, the top reaction's the cathode, the bottom reaction is the anode. So perfect, so cathode minus anode, so we get that the cell potential for this reaction at standard conditions is positive 0.43 volts. Perfect. So this reaction is spontaneous. It spontaneously moves in the forward direction. So just using that information, what should the value of K be? If this reaction is spontaneous in the forward direction, do you think K is going to be a small number or a large number? It's going to be big. Yeah, it's going to be big. So, but let's prove it. All right, so we have E cell. We need to calculate delta G. So the equation we use is delta G equals negative NF, the E cell that we just calculated. So we have E cell, F is a constant. We just need to get N. So we can use our trick again to figure out what N is. Remember, we're combining these two reactions. One involves 4 electrons, the other involves 1. So their lowest common multiple would be 4. So N is equal to 4 in this case, right? Or you can look at the overall reaction. We're going from 4 neutral silvers to 4 silver pluses. That requires losing 4 electrons. So N is 4 here. All right, so we have all the numbers we need. So delta G is negative 4 electrons, Faraday's constant 96485 coulombs per mole of electrons times the cell potential we just calculated, a positive 0.43 volts. All right, so what we'll see here is that the electrons cancel, and just trust me that a coulomb volt, a volt times a coulomb equals a joule. All right, so when we use this delta G equation and we multiply Faraday's constant by a voltage, we in fact get a joule out, just like when we typically use these delta G equations. And so I think what we get is a very large negative number. So it's negative 165.9 times 10 to the 3 joule per mole of reaction. And so this is also equal to negative 165.9 kilojoules per mole. And so yeah, delta G is a very negative number, and so we see, yes, this reaction is very, in fact, spontaneous in the forward direction. All right, since we have a positive cell potential come out, this reaction is spontaneous, this redox reaction is spontaneous in that forward direction. All right, so that's delta G. Now let's just get K, but that's straightforward enough. We've done this already, where if we know what delta G is, it's equal to negative RT natural log of K. In this case, what we're doing is plugging in those numbers. Make sure delta G is in joules, so negative 165.9 times 10 to the 3 joules equals, joule per mole, equals negative R, so use the 8.314 version of R, temperature 298, natural log of K. Natural log of K. Right, and so I'm just going to isolate that natural log of K. Natural log of K equals, let's see, negative 165.9 e to the 3 divided by negative 8.314 divided by 298. I get natural log of K equals 66.96. That sound right? Maybe. So a really big number. So to undo that natural log, we're going to take e to the both sides. All right, so e to that number I just got. Yeah, it's a huge number. It's 1. What we get is that K is equal to 1 times 10 to the 29. Yeah, so it's like a huge number. So we were right. So this reaction is spontaneous in the forward direction. We spontaneously make products. So this reaction will keep going until we approach K, where there's a ton of products present and not many reactants. Okay, so again, when we're at standard conditions, everything has a concentration of 1. So Q is equal to 1. But once we're at equilibrium, the forward and the reverse reaction are happening at the same time. When you're at equilibrium, your battery is actually dead because there's no spontaneous movement in the forward direction, if you want to think about it that way. When we're not at equilibrium conditions, the reaction moves spontaneously. We can harness energy from that. But if we're at equilibrium, if we have equilibrium concentrations, you don't have a battery at all because there's no spontaneous reaction in either the directions. Both are happening at the same time. And I think that's what the next question is, all right? Let's take this same reaction, and instead of being at standard conditions, having those concentrations, because we would measure a cell potential of 0.43 if we had 1 molarity of everything. But let's say, okay, you set up the same cell, so all of the concentrations, Q, is equal to K, 1.13 times 10 to the 29. Calculate the cell potential if that's what Q is. So we're going to use the Nernst equation here. We already have the cell potential at standard conditions. We know what N is. We're just going to plug in that Q. So let's just see what we get. All right, so what we will measure is equal to the standard cell potential, so 0.43, minus the concentrations that are there, 0.0592 over N. What did we say N was? 4. And then log of the Q. So we're going to set up this this reaction so it's already at equilibrium. We're going to set Q equal to K. So we're going to do log of 1.13 times 10 to the 29. All right, so let's see what we get. If you plug all of this into your calculator, 0.05, did I write it down? No, I didn't. 0.0592 divided by 4 times log 1.13 e to the 29. This whole term is 0.42998 volts, right? So that means what we will measure is 0.43 minus that. What will we get? 0. Yeah, it's basically 0. And so this is what we see. When you set up a battery, so you're already at equilibrium, that battery is dead, right? There's no spontaneous reaction going from one direction to another. If we're already at equilibrium, this is when your battery is dead, and you can calculate it. If you put in the value of K in for Q, you'll get a measured cell potential of 0 when you use the Nernst equation. These standard cell potentials are only when everything is 1 molarity, all right? And so that's how we can kind of include that aspect of K and Q into these concepts. Just like when we were doing delta G back in chapter 19, we saw, when we were at equilibrium already, delta G was equal to 0. That the reverse and the forward direction of the reaction were spontaneous. Both of them are happening. So we see, the forward direction isn't spontaneous. So delta G is equal to 0 when we're at equilibrium. And yeah, I think that's what I kind of summarize in this last slide, how delta G, K, and cell potential are all related to one another, in terms of those standard reduction potential tables. All of those tables are referenced from standard conditions. But remember, as reactions happen, these values of just delta G and E change because we're not at standard conditions. So the magnitudes of these different terms tell us something about the reaction. Typically, when we're at standard conditions and we use those table values, a reaction, the forward reaction is very favored, very spontaneous if delta G naught is a negative number. Typically, that means that K is very, very large, or your cell potential is a very, very positive number. That all happens with spontaneous reactions, including redox reactions. If we were talking about non-spontaneous reactions, a non-spontaneous reaction is going to have a delta G value of a positive number. K is going to be a really small number. E cell is going to be a negative number, right? That's what a non-spontaneous reaction would look like. All right, a reaction that's not a very good battery, right? But notice that all of these values, terms that I mentioned, these are the not versions, so these are at standard conditions. We don't have to be at standard conditions. Once a reaction runs, we're not at standard conditions anymore. So as a reaction progresses, delta G will eventually approach 0 because a reaction will always tend to approach equilibrium, because we know that Q always approaches K over time if we're not at equilibrium conditions. And what we see is that the measured cell potential also approaches 0, just because delta G approaches 0. But notice that the values of these delta G naught and E naughts don't change because those come from table values. But once we're not at equilibrium conditions and batteries no longer work, or your reaction already is at equilibrium, these terms at non-equilibrium conditions take over. So notice it's delta G and E without the naught, meaning we're not at equilibrium conditions. And then these are the equations you want to use there. All right, so cool. All right, so let's just do a couple more of Nernst equation stuff. Okay, so yeah, all batteries are voltaic cells. We typically look for cell potentials that are positive, but all batteries run out eventually, meaning that your measured cell potential, notice that I'm writing E without the naught, eventually approaches 0. That's when your battery runs out. And that's because a reaction's happening, the value of Q is changing, eventually E cell will be 0, meaning delta G will also be 0. Notice how I'm not putting the naughts there, right? Because those naughts come from table values. Okay, so let's do a couple more Nernst equation things, calculations, because I can promise you a question like one of these will end up on the exam, where I give you a reaction, a redox reaction, but I give you concentration. So we're not at equilibrium conditions, so there will be at least one Nernst equation question. But as long as you understand the Nernst equation, it'll be okay. Okay, so here we have a cell. Notice how I say calculate E cell. See, it doesn't have the naught there for this electrochemical cell. Notice how I'm doing line notation here. Line notation's nice because you don't have to do guesswork of what is the anode and what's the cathode. When we write line notation like this, it's always the anode on the left, cathode on the right. Because we want our electrons to move left to right, right? So there's my anode, there is my cathode. Here are my concentrations of things. Notice how the copper 2+ is 0.5 molarity. In our silver plus is 3 molarity. If this was standard conditions, everything would be 1 molarity, but it's not. So that means we have to use the Nernst equation and calculate Q. But remember, this Nernst equation, we still need the value of this redox reaction at standard conditions, so we still have to do cathode minus anode, but we can't stop there. We still have to account for Q. So if we look at this, copper is my cathode, silver is my anode. I can tell that from the line notation here, all right? So, oh no, I messed up. No, it's not. Copper is my anode. Anode, there we go. Copper is my anode, silver is my cathode. There we go. So that means it's going to be 0.8 minus 0.34. So I think my overall cell potential, if we were at standard conditions, would be positive 0.46 volts. But we are not at standard conditions. We're not at standard conditions. We have different concentrations. So, excuse me, we need to then use the Nernst equation. So we need to figure out what Q is for this reaction. So here I give you the balanced redox reaction. Q equals, so products over reactants, copper concentration over silver concentration, but it is squared. So now let's place in those concentrations that are actually given. Copper concentration is 0.5, and then silver is 3, but it is squared. So I think Q is equal to 0.0556. I wrote it in the corner. Right? So that's Q. That's what I'm going to plug in my Nernst equation. So I have E cell at standard conditions. I have Q. I just need N. So let's just take a look at these two redox reactions. How would you add them up? What's the lowest common factor, multiple of those electrons? It's going to be 2. Yes, so if we flip the anode reaction, but then we have to double the cathode reaction to make both of those reactions transfer 2 electrons. So here we see N equals 2 in this case. You don't actually have to do the flipping and doing the adding. You just have to think of what steps would you do to get them to match. So in this case, N is equal to 2. That's the minimum number of electrons I have to be transferred in this reaction for 1 unit of that redox reaction to happen. All right, so we got N, we got E cell, and then we got Q. So we just plug stuff in. So what we should actually measure in this reaction is 0.46 volts minus 0.0592 over N, so 2 log of that Q we just got, 0.0556. And so what we get is E cell is slightly different than our table value. It's closer to 0.5 volts when we pack a bunch of reactant into this reaction. We're pumping a bunch of silver plus into this reaction. All right, so that is your measured cell potential at non-standard conditions. In this one, it's between copper and silver. So let's just do one more. Again, doing non-standard conditions, but this one's a little bit different. So again, notice that I'm asking you to calculate E cell without the naught. So that means non-standard conditions. So we can't just do cathode and minus anode and be done. But we still have to do that, but we just can't be done. We have to include Q. So notice here, here's my anode. It's between copper and copper 2+. And here's my cathode. Huh. Between copper and copper 2+. Interesting. So if I tell you that the reduction potential between copper 2+ and copper is 0.34 volts, what should the standard cell potential be for this reaction? If everything was 1 molarity, what should it be? It's copper at the cathode and copper at the anode. It is 0. Yes, it's 0. But notice, we're doing cathode minus anode, we're using table values. This is if we were at standard conditions. This was if copper 2+ concentration was 1 molarity and 1 molarity. We would measure no voltage. Interesting. So what we're seeing is a concentration cell, because this reaction, this electrochemical cell is not at standard conditions. It has a different concentration of copper at the anode and a different concentration of copper at the cathode, right? So this is what we call a concentration cell. The overall cell potential is 0, so I know if we use the Nernst equation, this number is 0. But we actually have a number to put in for Q, all right? We just have to be careful here. How do we calculate Q? Notice we have some concentrations. Both of them are copper, so I need to figure out which one goes up top and which one goes on the bottom of my Q expression. So the hint for this is to write out your anode and cathode reactions, all right? When copper is oxidized, you are taking copper solid, you're making copper 2+ and you are giving off 2 electrons. That's an oxidation reaction at your anode. Then at your cathode, a different copper 2+ is taking those 2 electrons to make copper solid. Why am I writing this? It's going to help me figure out what copper goes up on the top of the Q expression and which one goes on the bottom. Because notice, copper 2+ is a product in the anode reaction, but it's a reactant in the reduction reaction. So when we calculate Q, the copper 2+ concentration in the numerator is from which electrode compartment? It's going to be the product. So this one's going to be coming from the anode. While in your cathode compartment, copper 2+ is a reactant. So that means copper 2+ coming from your cathode is going to be on the bottom, right? This is a little bit tricky, all right, to figure out what goes on the top and what goes on the bottom if I don't give you like a full-blown balanced chemical reaction. Do you see how I got that? All right, by writing out the 2 half reactions. Here's my oxidation reaction, copper 2+ is a product. Here's my reduction reaction, copper 2+ is a reactant. So that means when we actually calculate Q, what concentration is going to go on the top? 0.1 or 1? It's going to be 0.1. 0.1 is going to go on top because that is your anode concentration. So 0.1 over 1. So that means Q is 0.1. Perfect. Okay, so if Q is 0.1, I think what is N? N is equal to 2. And then we have our standard cell potential. So we have everything to calculate the Nernst equation. So let's do that. So what we should actually measure is our standard cell potential, so 0 minus 0.0592 over N, so that's 2, log of 0.1. And so when you do this, you get a measured cell potential of positive 0.0296 volts. Interesting. So we have copper as our anode, copper as our cathode. We are able to produce a tiny little voltage by just having different concentrations in those different sides. So this is called a concentration cell. You know, I think there are certain animals out there that can kind of produce these small voltages required for their bodies via just concentration gradients of reactive species like copper 2+ in this case. So yeah, we can produce a small, tiny little voltage by just having two different concentrations of ions in two different places. So I wanted to show you the example, because you'd think if you had the same substance as of your anode and your cathode, your cell potential should be 0. Technically, I didn't really even have to give you this value. It doesn't matter. They're both the same number, so a number minus the same number is always 0. But what generates the potential here is actually having a charge gradient, or a concentration gradient. So I wanted to show you this demo where the demo team very kindly walked over and carefully made this concentration gradient. So here, maybe you can see it's exactly this. It's a concentration cell where there's really concentrated copper on the bottom. I don't know if it's hard to see, but it's concentrated copper on the bottom and not so concentrated up top. Do you see that it's like it's more dilute on the top? Yeah, and so it's just having this concentration gradient allows for a voltage to be produced. So let's see if we can make this happen. I'll show you my camera to like prove to you that something's happening. Okay, let's see. Can we do that? Can you read this? Okay, see? So right now it's not connected to anything, so it's like reading 0. I touched it for a second, so it's reading very close to 0. Come on, read 0. And so now I'm gonna very carefully set this up. So you trust me that's reading 0, it's not connected, okay? So I'm gonna try to set this up. Oh, maybe I can do it like this. Can you read it? You can read it, right? No, you can't. Kind of. Okay, so that's 0. So I'm going to hook up these electrodes very carefully, and we'll see if you can see that potential produced just by having differences in concentration. Oh no. Hold on. Go. It was reading 10 earlier. Okay, did we see it increase a little bit? Just a tiny bit. Yeah, like 5 millivolts or something like that. Yeah. So it did increase a little bit once I hooked it up. And again, it's just by having it concentrated on the bottom to concentrated up top. What do we think will happen if I just mix this whole thing up? If I mix it all up, will there be a concentration gradient anymore? No. If I mix it up, how will the concentrations of the cathode and anode change? They're going to be the same, yeah? Okay, so they're going to be the same. So what should the value of Q be when I mix them all up? 1. Yes, if they're the same concentration. So what should the cell potential be? 0. So let's see if that happens. Maybe. So if I mix it up, hopefully something happens. Does it go closer to 0? Oh yeah, it did. Look at that. It went closer to 0. All right, and so by doing that, there's no longer a concentration gradient. So Q is 1. Your overall cell potential is 0. All right, no more. Yeah. Okay, so there we go. Okay, so there is the Nernst equation and how it can be useful. That, yeah, our anode and cathode can be the exact same thing, but if there is a concentration gradient, then we can force a potential to be there. Okay, so we have a little bit. So I want to just do a little bit of the VOL calculation that you're going to do tomorrow, because I don't want you to be completely lost. The calculation isn't too bad, all right, for the, I guess, the last part of VOL. So in the previous sections, we were always talking about, oh, I should just mention right now that everything we went up until right here, this is on midterm 4, all right? This is on midterm 4, okay? All right, homework 4, I think electrochem part 1 is now due, but it's not due until next Monday. Everything else past this will be on the final exam. I just want to go over, I'm going to take 5 minutes to go over electrolysis, because this is a part of VOL tomorrow and I don't want you to be lost. It's not that bad, okay? Because in the previous sections and what you'll be tested on Thursday, we're always basically spontaneous chemical reactions. We're always looking for positive cell potentials or positive reduction potentials. But if you look at, what is this, aluminum. Aluminum gaining 3 electrons to make aluminum solid. Is this a spontaneous reaction based on the value of this reduction potential? Is it spontaneous? Nope, it's negative, right? So this reaction is not spontaneous, but the reverse reaction is spontaneous if you flip it. Aluminum 3+, really hard to reduce. Aluminum solid, really easy to oxidize. And this actually had historical implications, okay? So like, you know how there's like the different ages, like, you know, the Bronze Age, all of that. Or like you think about the metals for like the Olympic whatevers, there's like bronze, silver, gold. But there was a point in time when aluminum was actually more expensive than gold, because aluminum was very hard to make. It was very hard to make. But now think about, is aluminum expensive? No. It is so cheap that we use it to wrap leftover food that we don't eat, that we forget to eat, and just the food rots in our fridge. So there's a point in time, so back right around the technology revolution, where the price of aluminum was super, super expensive. It was because it was really hard to make, because they didn't invent electrolysis yet. Most metals like iron, gold, silver, you just melt those ores down to harness the pure metal. But you can't do that with aluminum. They had to invent electrolysis to eventually do that. So the idea here is that this forward reaction is not spontaneous. It does not happen on its own. But what you can do is supply electrons via a wall socket to force that reaction forward. This reaction doesn't happen on its own, but you know, energy, like money, you have enough of it, you can do whatever you want. So if we supply electricity to this reaction, we can force it to go forward. And that's essentially what electrolysis is. If we supply the electrons to the reaction themselves. So how we calculate how much substance we can deliver is based upon the usage of Faraday's constant. So remember, this is Faraday's constant, where we said, okay, that 1 mole of electrons delivers this many coulombs. So this is where current is finally important, amps, where an amp, just memorize this, an amp is equal to a coulomb per second. So if I have something that's 5 amps, what this means is that 5 coulombs are delivered every 1 second, all right? And that's going to be really useful for us when we also have Faraday's constant at our disposal, where based upon Faraday's constant, 1 mole of electrons delivers 96,000 coulombs. This will be very useful to us, 1 mole of electrons. That's all you need to do. Understand, and then the rest of this is just advanced dimensional analysis. So let's look at it. Let's say we deliver 125 amps, so this is your current, to a reaction for 120 seconds. How many moles of electrons are delivered during this time? Well, let's start with that time, 120 seconds. All right. Remember what this current means. 125 amps means 125 coulombs are delivered every 1 second. That's what that means. So 1 second, 125 coulombs. Right? But if we were done, we'd be in the unit of coulombs. We don't want that. We want to be in the unit of electrons. So let's convert that into moles of electrons using Faraday's constant. So this is where we use the 96,000 number. But where's 96,000 going to go in this next fraction, on the top or the bottom? Bottom, yeah, because coulombs is up top right now. So this is 96485 coulombs, 1 mole of electrons. And then you get what? Tiny number. So like a fraction of a mole of electrons are delivered in this reaction, right? So let's do it a little bit backwards here. So I mentioned that, you know, there was a point in time aluminum was more expensive than gold. So much that when they were building the Washington Memorial, or Washington Monument or whatever, when was that? In 1884. Aluminum was super expensive, so the United States wanted to, like, you know, brag to the world about how great we were. So we took the most expensive material out there and topped the monument with that. So since the monument was built in 1884, the Washington Monument is actually topped with 6 pounds of aluminum, because that's what was expensive at the time, right? And so to, like, brag to the world about how great we were, we topped it with 6 pounds of aluminum. So let's calculate how many moles of electrons do we need to deliver to produce 6 pounds of aluminum. So in this case, let's think of it. If we start with 2,700 grams of aluminum, think about how aluminum is related to moles of electrons. Well, let's convert those grams into moles first. So we're going to use the molar mass of aluminum. So 27 grams of aluminum is 1 mole of aluminum, right? The idea here is, okay, how many moles of electrons are required to make that aluminum? Let's go back to this reaction. Look, aluminum comes from aluminum 3+. So for every 1 mole of aluminum, how many moles of electrons do I need to deliver? 3, yeah. So here, 1 mole of aluminum requires 3 moles of electrons, right? So we're kind of working our way backwards, okay? And so there's our answer. I think it's 300 moles of electrons. But let's not stop there. Let's calculate how many let's calculate how many seconds or hours it would require to deliver electrons to make this aluminum. So let's pretend we're running this at 125 amps. So if we wanted to keep going, we could say, okay, for every 1 mole of electrons, we have to deliver 96485 coulombs. If we were running this experiment at 125 amps, we could say, okay, 125 amps equals 1 second. And this would tell me the time it would take to make that much aluminum if we wanted to keep going, and I gave you an amperage. All right, so really to do the electrolysis part of the VOL lab, really what you need to know is the unit of amps and how to use Faraday's constant. And all it is dimensional analysis, all right? Okay, so we'll stop right there. You have everything you need for chapter or midterm 4. Let's take a 5-10 minute break, and then we'll have the review session. Of course, you don't have to stay if you don't want to. I will be recording it. So let's take a little break. Okay.